to introduce him. Yeah, Dr. Ram Prabhu has done his BTech metallurgy from NIT Tiruchi in 2005. After that, he has done ME in IIC Bangalore, okay, in 2008. After that, he has joined for his PhD in Engineering Design Department, IIT Madras, and completed in 2014. Okay, he has vast experience, more than 12 years in research field, and he is a scientist. He and Joint Director DRDO from 2009 onwards. He's like secured many awards and fellowship. If I start to read that, itself takes some time. Okay, couple of things I'll just say. He's a recipient of prestigious Young Alumni Achiever Award 2016 from NIT Tiruchi has received. Then recipient of prestigious gold medal and commendation certificate from the Chairman DRDO in the National Science Day in 2017. And then recipient of Bharat Gaurav Award in 2016 from IIFS, so on. And then he has like published more than 45 journal papers in international as well as national journals. Apart from that, he is having a collaboration with many institutes, and namely like Anna University, IIT Vellore, Kalasangam University, and then IITs also. He authored around 6 or 7 book and book chapters. Apart from that, Sir is having professional membership in few bodies like life member of Society of Failure Analysis, a member of Bureau of Indian Standard, okay, and then I am member for International Association of Engineers Hong Kong, so on. Okay, with this short introduction, I request Dr. Ram Prabhu to address the participants. Over to you, sir.
Thank you, sir. Thank you so much for the introduction. First of all, I thank Dr. Ganmani and Dr. Kesavan for giving me the opportunity to share my thought process in metal 3D printing. So I wanted to focus my application into the aerospace. Sir, how long I can take, sir? About an hour is okay, sir?
Yes, sir. Yes, sir. It's scheduled for 2 hours. But based on your timing, please go ahead, sir. No
yes, sir. Okay.
Yes, sir.
Okay. Thank you, sir. Thank you. So I just want to cover in this presentation about what is a commercially successful additive manufacturing process, that is laser powder bed fusion. How in the certification, what are the parameters we expect manufacturer to capture, and what are the avenues for the research for the academicians I want to cover at the end, which as a certification agency or as a development agency, we look for academicians to contribute in this area, either in the form of their PhD research or some funding proposal, so that those data, whatever you generate, it will help us in the long run to establish this technology into several applications in aerospace. So I think this is the last session, I know. So you had a lot of technical session in this metal additive manufacturing from the different experts, and they have given great insight into the process. So I'll not get deeper into that. I'll just slightly touch upon some of the important points in the metal additive manufacturing. Then I'll directly give what are the applications targeted in aerospace. So as we all know well, CAD drawing is the one which is the input to the 3D printing machine, which will help us to build the 3D printed part by progressively adding the layer by layer, layer upon layer materials. And there are a variety of sources are used: laser, electron beam, electric arc. So out of which laser and electron beams are beam based machines are very popular. And particularly looking at the market of additive manufacturing in India, laser-based machines are more popular than electron beam machines. And these high-energy laser sources are used to locally melt the metal powder in a protective atmosphere. Otherwise, it will lead to oxidation and other problems. And along the path as guided by your CAD model, and you melt the metal and rapidly solidify. And we keep repeating this step by building layer upon layer, we will evolve the three-dimensional component. So broadly, ASTM classifies this process into two categories: powder bed fusion, where the powder is the raw material and is spread on the bed by using the laser or electron beam. You will build the component. Another one is direct energy deposition, which uses slightly higher energy, and either wire or powder is used as a feedstock. And again, the laser or electron beam can be used in the directed energy deposition. And commercially successful process, if we see laser powder bed fusion, is ruling in India in the aerospace sector for building several components. Different companies call him different name, like selective laser melting, direct metal laser sintering. So SLM technology, SLM solutions, they call SLM, and US company, they call DMLS. Fundamentally, if you look at it, it is this process is evolved from combination of welding and powder metallurgy processes. So let's have some idea about what are airframes in a typical aircraft and helicopters, and what are the components we can target in 3D printing. So a typical aircraft airframe, we generally see, or classify the structure into wing, fuselage, horizontal and vertical stabilizer, and then landing gear. And coming to the helicopter or chopper, we have a fuselage, and we call it the backside as a tail rotor system, and you have a skid landing or the wheel landing, and primary rotor systems. So if you look at the main rotor blade in the helicopter, it's made up of titanium with the composites, and most of the bodies in the airframes are carbon fiber reinforced plastic or carbon glass fiber reinforced plastic. But the location wherever the high critical stresses are coming, and where the loading or fatigue and tensile, where metallic components are generally used, preferably aluminium. Very rarely magnesium is used. Magnesium is widely used in the helicopter where the vibration comes high. So otherwise the aluminiums are more preferred because of the process complexity in manufacturing magnesium. Either forming route also it is difficult to form, and casting route also it has its own challenge, like it has a fire hazardness. So aluminium rules in a metal area in a typical airframe. And most of the elements, if you see inside the wing or fuselage, a lot of channels and structural elements are there. Those flanges, casings, all those things are most potential components that can be 3D printed in coming days. So currently these are manufactured through some of the forming processes or directly machined from the feedstock. And let's look later the skeleton structure of each parts in the airframe, looking at the wings or vertical stabilizer or fuselage or landing gear. So you can see several elements, they are called in different names, but most of them are either, if it's a stress critical component, most of them are aluminium based elements like longeron and stringer, rib, spar, and so on. And similarly, if we come to the landing gear at the right side, you have a landing gear. Most of the landing gear parts, like nose or main landing gear parts, like actuator, cylinder, most of them are metals, either of aluminium or some areas we use the titanium. So wherever you have the complex in shape, where additive manufacturing can play a big role in coming days. And coming to the aero engine, that is the heart of any aircraft. The top one is the jet engine, the bottom one is the shaft engine. So the jet engine is typically used in the aircraft, and turbo shaft engine, it's widely you find it in helicopters. So the functions are you suck the air and compress it, and you expand it in the with the fuel you burn it and expand it in the turbine to generate the energy, and at the same time the thrust. But looking at the temperature and pressure inside that typical aero engine, it goes like this, like when it enters maybe a sub-zero temperature in the fan region, it is close to 100 degree. Then when it enters to the compressor, it will be in the order of 400. I mean, you have a different stages of compressor, so you have a progressive increase in temperature. And in the combustion chamber, the temperature goes about 1500, 2000, and the turbine entry temperature will be the order of 1200. So then it goes as a exhaust. So if you look at the different operating conditions are prevailing in the typical engine. So that is the reason if you see fan, it's generally made out of aluminum alloys, and rare end of the fans are usually titanium, mainly titanium 6 aluminum 4 vanadium. Then comes to the compressor. In the compressor, the first stage to the close to the last stage, you will find typically a titanium alloys, that is to either titanium 6 aluminum 4 vanadium or titanium 6 ZRD. Both of them are alpha beta alloy. And the rare end of the compressor, you will find some super alloys. The combustion chamber again is super alloy. Turbine regions completely ruled by super alloys. Then the exhaust regions again a titanium alloys. So if you see the complete engine, 90% of the materials are either aluminum or titanium or super alloy, and some regions wherever the gear component, transmission components comes, there you find some high strength steels. So unless airframe only 30% are metal, here about 90% are metal, and all of these components are complex in nature. The tolerance required to for the aero engine components are highly sophisticated. So this although throws a challenge, but it also gives an opportunity for the novel process to take over the conventional process. So if you look at the conventional process like vacuum investment castings or the powder metallurgy, the problem with these all the processes, one is the acceptance rate. Any component if it develop in the aero engine or for the aero engine, the acceptance rates somewhere around 30 to 40% because of the stringent NDT requirements, the defect tolerable limit. At the same time, higher property requirements, especially high temperature properties and the dynamic property requirements. These either it fails in the testing stage or it fails in the NDT stage. So the acceptance rates comes closer to 30 to 40%. And similarly, yield of the process, if you see, that is also very poor. If you are directly machining from the bar stock, it will be only 5%. And if you use casting forging, castings also very low, like 30% will be the general yield, and forging a little higher, maybe 40 to 50% you can make out. But in all the processes, the problem of high buy to fly ratio exists in the traditional process, which can be solved through the 3D printing kind of process, where you reap the benefit of low buy to fly ratio. Just to show the skeleton of the aero engine, the red color regions are supervised. You see the composition of the metal usage in the typical aero engine cross sections. As I said here, like in the fan region, aluminum you find, then compressor region you find titaniums, then you find the super alloys ruling from the compressor end to the turbine end. So we will just look at it, some of the potential components which is very promising through 3D printing. Nozzle guide vane, it's a static part which has a complex cooling channels and the complex designs. The thickness is also very less. And this is a static part, and turbine blades are rotating parts. Again, you have a cooling channels, and some of the turbine plates are single crystals or columnar grain structures. These columnar grain structures are easily attempted through 3D printing. I mean, there are some studies from US wherein they show that single crystal also is possible through 3D printing. Similarly, the turbine disc, a massive component with the integrated blades and disc blisk we call it. So those these components and the combustion chamber and fuel injection nozzle which is used in the combustion chamber, these all of them are shape complexity is high, and the requirements also the requirements means in terms of the NDT or in terms of the property or requirements are very high, which can be easily realized through 3D printing. And coming to the gear transmission components in the aerospace, especially a typical aircraft, you see that aircraft mounted accessory gearbox, which consists of about 10 to 15 oil lines, which is running from one end to other end, about half-meter length. Oil lines are running. Some of the oil lines are buried inside. Okay, it's like a blind oil paths will be there. So these are presently manufactured through sand casting route because of the massive size and the complexity. The yield is 15%. Acceptance rate is very poor. That is even 10 components. If you make only one component passes, it fails at some of the regions. One is either the dimension issue comes, or the oil passage issues, or defects at the oil passages junction. So these are the major reasons for the rejection of these gearbox casings. Similarly, helicopter gearbox, which is also very complex shape, and wheel hub. So these components are can be can be manufactured to 3D printing instead of the traditional process to reap the benefit of 3D printing. And some of the sheet metal components, and if you see, several components are assembled together and joined through secondary process like welding or brazing. So these are some of these components can be easily developed through 3D printing as an integral single components. And some of the components in the aircraft like impeller, which are directly machined from the bar stock due to the complexity of the shape. And if you take these cases, it's 100 kg metal bar stock is taken and machined to get this impeller, which is a 5 kg. So you can see 95 kg of the materials are wasted. So such a poor yield process can be replaced with 3D printing, as well as the complex shapes files can be easily achieved through 3D printing. And the instrument panels, which are non-stress critical. Okay, so these and of course it has a complex shape, so this can be easily made through our laser powder bed fusion kind of 3D printing process. And few more fuselage, bionic fuselage, fuel injector nozzle, which has the nozzle dimension in the order of micron meters, and some of the actuators, cylinders, and turbo shafts. These are the other potential components in the structural components in the aircraft, which can be fabricated to 3D printing. Few more, like these are the components already demonstrated by Westerners in their aircraft applications, like fuselage panels and sensor assemblies, sensor holders, temperature sensor, and so on. See, these all the structural components are non-load bearing members, but having the complex shape, has at certain different functions, and which can be achieved through 3D printing rather than the conventional processes. So looking at the global scenario in the 3D printing, like in direct energy deposition or powder bed fusions, these are the companies who has established the brand in the 3D printing. Okay, so if you see in the direct energy deposition, DM3D is a very famous company. Their machine is their technology is called direct metal deposition. Optomech, they call it lens, that is laser and engineered net shaping, and Shaki, they call direct manufacturing. In these all three processes, you use the metal powder and laser as an energy source to melt and deposit to get a component. Whereas there is one more process called wire arc additive manufacturing. Originally, it was developed and patented by the Rolls-Royce. Okay, and it uses metal wire and electric arc as an energy source too for the melting and deposition. It's a customization from conventional gas metal arc welding process. And coming to the powder bed fusion, again laser or electron beam. There is only one company who uses who is popular in making electron beam additive manufacturing machine, that is Arcam. Currently it is acquired by GE. Okay, rest all the company uses laser. Different company calls a different name, but the process more or less same. So 3D System is one of the popular company. They call it selective laser sintering. EOS, which has a very huge market share in India. They call it DMLS, direct metal laser sintering. Renisha, the company they call laser melting. SLM Solutions, they are the second best in India. Their machines are called selective laser melting, and concept laser machines are called laser press. Just you have a computer make a CAD model and send convert it to the STL file, then it send it to the machine. Machine fabricate the parts depending on the part geometry. The supports are given. Supports are generally printed with weak properties so that it can easily remove. So looking at some of the advantages, so first and foremost is the design flexibility or the freedom. So any complex and customized shape can be easily entered through manufactured through 3D printing. This has a saying on the weight, that is a part weight reduction is one of the consequences of this design freedom. In the aircraft, even saving 1 kg of material in a typical aircraft saves a lot of fuels, which results in not only the cost saving as well as environmental pollution reduction also. And similarly, you can consolidate the part and make a single component, so you can reduce the number of parts in a typical assembly. Okay, this not only reduce the lead time to manufacture the component, also very important problem pertaining to the users, that is the inventory storage. So it minimizes the storage of the inventory of spares, and also it avoids the joining processes like fasteners or welding if you are able to make the integral components. So yeah, so low buy to fly ratio, which is nothing but like weight of the raw material used to build the part divided by the weight of the final component. So this shows that there is a huge material saving, which results in huge cost saving. And of course, the powder, whatever you use, has an excellent potential for recycling and reuse. And functionally, if you look at it, you have there is a ability to develop a heterogeneous material like functional gradient material or a composition gradient, and so on, so that you can tailor the parts with location specific properties. As a process by nature, there is a repeated heating and rapid cooling and heating and cooling, which results in extremely fine microstructure with no elemental segregation in the part due to the rapid cooling rate, which is experienced in 3D printing. Of course, any process comes with its own challenges. First and foremost challenge, anisotropy. Properties varies with the direction due to the grain orientation. And second challenge is residual stresses because of the rapid heating and cooling. And unfamiliar defects. When I mean unfamiliar, these defects are very peculiar and specific to the 3D printing, which they are not experienced in the conventional process. So you don't have a standard or specification which can help you to identify these defects, or there is no standardization in that. Currently, machine costs about few crores, 2 to 8 crores. So high capital investment. But when you look at the production rate or the production volume given by this one machine is comparatively lesser than the traditional process. Of course, there is this process is evolving in India. I see it like 2017 it started picking up, and it's now in a rapid phase. It's growing, but still, if you look at the material characterization, there is a state of the material characterization is still immature. Although it's a challenge, but it is a boon for all the academic researchers, because they are the one who are going to help us in developing the data like microstructure, grains for different materials or new materials, and so on. And for the industry people, yeah, there are still a challenge in standardization, and there are challenges in specification. For example, Ti-6-4, titanium 6 aluminum 4 aluminum, there is a heat treatment in the conventional standards. But whether the same heat treatment is applicable to the 3D printed component, if we ask, we can't say surely that that is the best heat treatment for the 3D printed component, because your input stock, that is a 3D printed state material itself has a different microstructure. when you try to implement the traditional heat treatment, I don't think it is going to get you the similar microstructure what you get in the traditional process. Of course, the testings and the NDT standards still both of them are in infant state. Like, let's say if I do fatigue test on the 3D printed component, the fatigue testing scheme which for the 3D printing component is entirely different. Like, because you have anisotropy and which location you have to take a sample, how many number of samples to be taken, these informations are not clearly standardized yet. And similarly, NDT, your X-ray radiography or UT is not the best technique to identify the defects in 3D printing. That is a very recent people are going for a little advanced one like X-ray CT, and recently there are some research in laser ultrasonic methods to characterize the components for the defects. Of course, there is a challenge of high cost due to the low production volume or low build rate and limitation in build volume. So what I understand, like in EOS machine, you have about 400 into 400 into 400. So I don't see any machines which has which can build a component of 1 meter. Till now, I have not come across. So there is a challenge or there is a limitation in the build volume, and similarly the build rate or the process speed. So let's say to evolve a component of 100 mm by 100 mm by 100 mm, it takes few days. Whereas in castings or forging, if you see, it's hardly about hour to get the component final components. And the surface roughness is one of the major issue in the 3D printing, especially when you have complex shapes. And currently, what I understand, about 10 to 15 alloys are only standardized for printing. So when I mean standardized, for which the optimized process parameter is existing, still much more to come. So that is a boon for the academic researchers. So looking at the certification point of view, how in India we do, suppose most of our aircrafts are flying with the components process by traditional process with a different material grade. Let's say I take a beta titanium alloy and I don't know a powder of beta titanium alloy so that I can 3D print it. So I have to map it with what I have in 3D printing. So what we do generally, we take a component, we understand what is the original grade and what is the tensile properties, and we map it with the 3D printed grades. Chemistry most of the time doesn't match, hence we only take a chemistry to understand whether am I choosing the similar kind of material. Titanium means titanium, aluminum means aluminum, steel means steel. For that reason only chemistry is needed. Whereas tensile property plays a huge role, wherein I'll try to fit the tensile property. Most of the time what we find is if strength is high, ductility is less, or other way. So we try to map it and see that the variations are less than 5%. Then only we fit it, otherwise we don't fit the equivalent grade. Okay. And next we look at it, 3 aspects of the functionality of the component. What is the load acting on the component? What kind of magnitude? And what is the temperature of the exposure? What is the operating environment, especially the corrosive environment? So in the first phase, I have identified a particular 3D printing equivalent grade. Now, based on this data, especially the fatigue loaded components, we look at it, what is the temperature it exposed and operating condition, what is the load. Now we will map, we will try to understand in these aspects whether this equivalent grade is okay or not. Then design philosophy, whether it is a fail-safe design or safe life design or damage tolerant design. Fortunately, most of our aircraft are either fail-safe or the safe life. We have not started using the design philosophy of damage tolerance. So we generally play very safe in the aircraft design. So this also we look at it, and the functional testing of the component. Whether this component what I'm going to print, it's going to undergo any functional test or not. If a particular functional test, like for example, like spin test, overspeed test, and so on, there are so many functional tests. So whether it is there or not, we will see, which will help me to understand how critical is the component. If it is highly critical, then I'll be very cautious in choosing the equivalent additive manufactured grade. Then the post processing, like coating, plating, machining, painting. See, most of the time what we understand, like for example, we have printed few years ago aluminum tanners engine, and in place of A3/7, that is aluminum silicon, 7% silicon on it. When we do the anodizing failed on the 3D printer. The reason is presence of the silicon disturbed my anodizing. This we came to know later point of time only, and within my 4 to 5 months we fixed that problem. But the idea is whatever the post processing we implement on the traditional process may not work in the 3D printer. So there also we will face a challenge. Of course, what is the type of AM process? Currently we use only laser powder bed fission, but looking at the long distant, in future electron beam based or the direct energy deposition based process also will come into pictures. These are the factors we look at it before freezing the equivalent materials in 3D printing for a particular aerospace components. Next is, let's say I have freeze the 3D printing grade, like let's say titanium 6 aluminum 4 vanadium. How do I do the how do I ensure that the part which is airworthy? So I will start from the feedstock, that is a powder. These are the properties I will check, freeze it. That is very important, because when I freeze it only, I can ensure the consistency in the next batches. For example, size distribution, shape, surface texture, flow rate, apparent density, tab density, all the gaseous elements, powder chemistry with the trace elements, and true density. So the bracket, what is the instrument is used to get these properties. We freeze each and every parameters in this, and unless each batch or each lot meets this freeze requirement, it is not allowed to be used to build a component. Next comes the process. So there are about 100 plus parameters are there. So major parameters brought out here: laser power, scanning speed, scanning strategy, build direction, build substrate temperature or powder temperature, layer thickness, hatch spacing, ambience what we use, whether nitrogen or argon or any other ambience, powder flow rate and moisture content. Then there are some parameters about the recoater blades, other sensor based informations. We capture everything during the first development, and if the first development is successful, that will be freezed till the end. That one, as long as we follow that, then only the certification will be awarded. Then the process document. So we look at the process parameter freezing, and there are other aspects also you have to look at it, like process control document, which broadly covers what is the AM machine and the make. For example, you build a component with the EOS machine, and tomorrow you are going with the SLR machine, then the entire thing will change. Or different other processes like direct energy deposition. Similarly, the build strategy, like how the build orientation, and the raw material source, where from you buy the powder, post processing, and during the build, did you intentionally stop any or any unintentional stop? All the things should be captured. Then the way in which the build support structure oriented or the part oriented with respect to the platform should be captured, and machine serial number, build number, different machines of same brand or specification used to print a part. Then your operator who print this material, whose approval procedure, then all the sensors, machines, laser system, calibration status, all the software, hardware updates to the machine, and calibration is required if any change in any of the things, like the metal powder or it is not properly calibrated, like every 6 months is defined. If they are not calibrated, then they will be forced to do the calibration, then only they are allowed to print. So as a certification, we will look at all the points, okay, for the every part development, so that we ensure the consistency of the build or the quality of the component. and defects, which are the major challenge in the 3D printing, and which is the one we give more emphasis in the certification. So there are about some 6 defects I brought out here, which are very prevalent in the 3D printing, like porosities, hot cracking, unmelted particles, surface roughness, oxidation, and some bald surfaces. And we typically use X-ray CT scan at this point of time for the internal defects, FBT for the non-magnetic materials, MPI for the, that is fluorescent penetrant, another one is magnetic particle inspection for the surface defects. So these are I just wanted to introduce you, and the next is area which I want to propose to you. It is a more of a discussion. I just want to bring out my thought process to the academic community so that you will help us in this mission of establishing this process for our country. So I just want to bring the idea like what are the material grades currently available with the companies and which application it's used or which industry it's very popular. If you look at in the aluminium alloy, I'm finding it 5 grades are very popular. Aluminium 10 SiMg, aluminium 12% silicon, aluminium 7% silicon or A356. So these aluminium silicon alloys are cast alloys easily printable for which process parameters are already optimized. And recently, there is a company called EOS. They have come up with an alloy called 2024 aluminium copper alloy with certain ceramic particles are there in that. So we can call it as a metal matrix composites. RAM means reactive additive manufacturing. You'll have elemental particles, elemental powder with the metal. But during the additive manufacturing, the reaction happens such a way that you will find the particles in that. Then there is an alloy called scalm alloy, that is aluminium, magnesium, scandium. These are the alloys for which 3D printing is easy and the process parameters are optimized. Coming to the titanium alloy, these are the powders are available in worldwide from the powder manufacturer for 3D printing. Aluminium, titanium 6 aluminum 4 vanadium. Gamma titanium aluminate and commercial pure titanium and titanium, aluminium, molybdenum, vanadium, chromium. This is a kind of alpha beta titanium alloy. Then titanium 6242, again alpha beta titanium alloy. Then the beta titanium alloy called titanium 15 moly, 3 aluminum and 3 neodymium. This titanium is very popular in the compressor sections of aero engine as well as some of the bio implants are used. In the dental area, you will find cobalt based alloys like cobalt chromium moly or cobalt chromium tungsten or cobalt chromium for which powders are existing. And in the aero industries, for example, fuel injection nozzles are made out of cobalt based alloys. And some of the maraging steels like 16 Ni400 or 18 Ni300 maraging steels are widely popular in aero industries for which powders are existing. You can 3D print it. In tool industries, recently people have introduced, the 3D printing community have introduced H13 tool steel powders. This is easily 3D printable. And low carbon, low alloy steels like 20 Mn CR5 and 4 series steels. That is called nickel chromium moly steels. These are very popular in the automobile and the aero industries. Then high alloy steels like 17.4 pH or 15.5 pH or stainless steel 316L, 420 ferritic and custom grade steels for which powders are existing and people have printed components reliably which are used in the aero and bio implants. And aero engine turbine regions and combustion regions mostly you find super alloys. So about 5 super alloys in the inclinal area. Powders are available. It can be 3D printed like 709, 625, 713, 738, 939. Nitinol, that is a popular shape member alloy for which powders are currently existing. And it is used in the aircraft actuators and pipe couplings. So this is also 3D printable. And recently researched alloy called CM247, one of the popular high temperature super alloy used in the turbine regions. This powders is available, people have printed. and cast alloys, again in the aerospace industries, in semiconductor industries where the heat sink material, like copper based one, tin bronze or aluminum bronze or chromium bronze are very popular, and currently people have started printing these copper based alloys also. Jewelry industries, all noble metals like gold, silver, platinum, palladiums. Similarly, in the imaging devices, which uses a tungsten, which is 3D printable currently, which is used in the medical industry. So these are the alloys. You can start working on it, build the data on it. So what data, what we look at it, I am going to cover in the subsequent slides. Let's look at it in the designer point of view. In which scenario aluminum alloys are chosen by the designer in the aircraft. When a particular component of the system, if it is not exposed beyond 120 degrees Celsius and the load coming on the component should be less than 250, then designer chooses aluminum alloy. So I have given a couple of applications which I have shown you already also. You can just read out that. So what are the research area you can work on? Aluminum alloys are difficult to print due to the poor absorbability or high reflectivity or scattering. So you can work on finding out the best laser which can give you the better absorbability for the aluminum alloy. So that one problem is very interesting one. Second is precipitation hardening. So aluminum alloys are strengthened with precipitation hardening. But 3D printed alloy is already a quenched state. Do I need solution treatment again, or directly I can go for aging? There are some studies which shows that T5 treatments are better than the T6 treatments. So still lot more can be done in precipitation hardening heat treatment area for the 3D printed aluminum alloys. And recently I came to know that 7050 alloys are 3D printable. But if you look at the 7 series alloys, all of them are prone to stress corrosion cracking. And based on the heat treatment what you use, whether T73 is needed or not is still not known. So these area you can channelize your research and gather the data and let us know, like industry, that stress corrosion cracking is important for 3D printed armor. And most of the aluminum components which are high load bearings are susceptible to fatigue, mainly high cycle. And understanding the high cycle and fracture toughness are very important. So I use data generation on this area is the order of the day. Then pitting corrosion is another issue. And the schemes which you use to protect the aluminum alloys like anodizing and chromatizing. These area studies are very much needed. And developing the nano grain structures is possible through 3D printing. There are some reports already available by some German researchers. So those areas you can think of. And currently aluminum alloys are used up to 120 degrees Celsius. By using Scalm alloy or RAM 10, it is proposed that aluminum alloy's working temperature can be improved or increased to 200 degrees Celsius. So you can channelize your work on how to identify the grade and the heat treatment which can help you to use this material in a much higher environment like 200 or 250. And the process map design is one of the important area which we should work on and develop a process map for each and every grades. For example, in forging, you have a beautiful book from IITPKD Prasad and the team, like which will tell you which location or which process parameter domain you should work or which area, which domain should not work, which leads to the defects. So those kind of process map should be evolved. And some of the applications which involves fritting in the aluminum alloys, hence the fritting wear studies are very important. Similarly, most of the gear components are undergoing lubricating wear. So, and all of them are mostly aluminum silicon based alloys. So, lubricating wear studies are important. Of course, the erosion studies are also important because oil is flowing through that. I just captured all the numbers, just put it. I'm seeing about 77 ideas can be explored in this area. Looking at the designer perspective, where the titanium alloys are chosen, wherever the temperature doesn't exceed 500, stress level less than 500 MPa. Similar application like aluminium in the hypersonic aircrafts and most of the engine compressor regions, pylons, and some of the missile parts where these titaniums are very much used. Titanium by nature forms a texture during any forming process, and as we all know, forming certain kind of texture, either you can have a texture hardening effect or the weakening effects. And this process, by virtue of its nature, also forms a texture grain orientations. So understanding the developing a texture understanding on this titanium alloys 3D printed one is a paramount importance. And titanium alloys are strengthened or the properties are tweaked through the solution treatment and the aging, which involves formation of size, a different size and morphology and fraction of alpha or beta phase or the martensite phase. So in the as printed state, what I understand mostly we see martensite phases, and the conventional solution treatment aging may not work for the 3D printed one, and there are a lot of scope for the researchers to understand the heat treatment effects, mainly the solution treatment aging or annealing treatments on the 3D printed aluminum alloy, and you can tailor a specific heat treatment which gives you most optimized properties for the 3D printed one, which is an expectation from our industries. Because currently standard says something, few standards are available, but I am sure there is a gray area which can be easily attacked by our academic researchers to come out with a novel heat treatment scheme for the 3D printed cluster alloys. And certain environment titanium alloys are prone to hydrogen embrittlement and stress corrosion cracking. So you can look at in that area. And most of the components, titanium components in the aero engines are undergoing low cycle fatigue. So studies on the fatigue and fatigue crack growth or corrosion fatigue studies are very, very important. The data are currently not available. This puts a serious restriction on certification agency or the development agency to select these alloys for the fatigue critical applications. As these alloys are used up to 500 degree, of course, creep and stress fracture is very important. So data is not available. So I urge all the academicians to focus their energy on developing this data. And most of the aerospace components are complex in shape, and by virtue of the process nature, it is meant for the complex shape. So conventional smooth samples data may not be that relevant for the complex shapes. So it is important to study the notch effects, which will mimic your and which will help you to understand the complex shapes effects on the or geometry effects on the properties. So create a notch with a different stress concentration and study its behavior on tensile or static mode and the fatigue or dynamic modes. Gather the data, which is very, very important because titanium alloys are notch sensitive in nature. And titanium alloys are prone to hot corrosion in a different ambience. So conventionally processed like rod grades, you have all the data for hot corrosion and oxidation, but 3D printed, it's still evolving. Of course, like aluminum alloy, you can work on process map studies and fitting wear studies because your disc and blades you coupled by loose fit, those areas are prone to fitting, and titanium alloys are some of the regions it's coated. So conventionally processed titanium components with a conventional coating may or may not work with the 3D printed one. So those areas needs attention and to be explored. And hot erosion studies. The compressor regions which are close to the combustion chamber are exposed to the hot erosion. So studies on the hot erosions also to be done, and those data are also very important for our industries, designers or certification agencies. And these ideas, whatever I had given, it's very well welcomed by all the project funding agencies because they want industry importance work. Going to the next level, that is a nickel or cobalt based superalloys. So when the temperature is in the order of 1000 and stress at the temperature is less than 500, typically superalloys are used. like a combustion chamber, turbines, casings, nuclear reactor components, missiles, heating elements in tool and die industries, like tools and dies in the metal forming industries are usually a superalloys. And superalloys to improve its temperature performance, they generally coated with thermal barrier coating. In addition to that, they make it as a single crystal, and cooling channels also introduced. So the conventionally used TBC is applicable to 3D printed superalloys are the subject of debate till now. So we can work on those area and develop a TBC for the superalloys. And similarly, these alloys are strengthened, or its creep strength or fatigue strengths are improved by the precipitation ordering treatment. So we form several ordered precipitates like gamma prime, and several undesirable phases like topologically closed packed planes and lava spaces. And the morphology and the fraction of carbide phases or borate phases are very important. So these in the conventional process, the way in which you get definitely different in the 3D printed one. Okay, so understanding the precipitation ordering treatment on 3D printed components is paramount importance. So I urge people to focus on the heat treatment studies on these superalloys. And there are some reports which states that columnar grain design is possible through 3D printing, which if we achieve in India, definitely it will be a great achievement because it will help to improve the creep strength. Of course, low cycle fatigue, crack growth studies, thermal fatigue is another area where we should importantly focus on superalloys. All high temperature properties like hot tensile, stress rupture, creep studies data are very important in superalloys. And in the design perspective, how innovatively I can make the cooling channels to improve the efficiency of the cooling in the hot end parts. And hot corrosion studies, again, like a titanium alloys, oxidation studies, hot erosion studies, fitting. Because one side titanium, another side is superalloy in the air engine. So all of them are more or less same. And process made design for existing and the new grades. This is common for all the grades. Steels, although not so popular in aerospace, but still we use the high-end steels in the aerospace applications. When the system is not exposed to less than, not exposed to more than 300, and stress levels are in the order of 500 to 1200 MPa, and if the environment is not so aggressive like the corrosive environment, then steels are generally chosen. So most of the components you find in landing gear, high stress critical regions like slat tracks, door plugs, wheel axles, and so on. All the gearbox, transmission, high strength parts like PTO shaft, power type of shafts, actuator systems, gear pinions. Chemical processing industry mostly finds stainless steels. Surgical tools, stainless steels again. Tool and dies, where we find some high temperature resistant steels, and high-end automobile parts. So one of the area which we can think of studying is quenching and tempering areas, because in this process itself you get the quenched 3D printed component. Whether do we need to do once again quenching, or how about its tempering effects? All those regions we can touch upon and understand the different phases formation by different heat treatments in the steels. And all the gear, landing gear parts are subjected to both low cycle and high cycle. So fatigue. So getting the fatigue data on these alloys are very, very important. So here you have to fix the material, you have to fix the heat treatment, you should have a clear understanding about the phases, then you do how to conduct the property characterization. Otherwise the data will have a huge scattering. Steels are generally prone to various forms of corrosion, so studying like electrochemical and stress corrosion cracking hydrogen implements are very important, and the schemes like coating or plating to avoid or minimize or delay need to be studied on these 3D printed steels. And impact studies are another important, because steels are prone to ductile to brittle transition, and steels are notch sensitive. So similar like titanium, we should also understand the stress concentration effect on these steels. So till now we have seen on the material specific. Now let's look at the process specific. What are the things we can understand, write a proposals or a study on that. One is the powder. Okay, so as you know well, spherical particles are the one which is needed for the laser based powder bed fusion, because of the flow rate requirements and the packing density requirements. Similarly, the particle size also should be in the range of 15 to 60 micron meter as defined by different companies. So understanding the powder size distribution shapes affects on the properties and the defect formation in the component of paramorphic products. There are some talks wherein they say even water atomized powder can be used to get the similar properties achieved by the spherical particles. So this area is still a gray area. There is no complete understanding on this. So I urge people to study on powder effects or powder property effects on the final component property of the defects. And similarly, inert gas. Presently, we find most of the components are printed under the ambience of argon. How about nitrogen, which is less expensive? And I expect the similar efficacy is there with the nitrogen. So how about its impact on the properties and defects? There are some studies says nitrogen is much better than the argon in steels. So, but still there is no clarity. It may be the case that nitrogen may be more akin to some grades and argon may be more close to some grades. So we need to understand this inert gas effects on the properties and defects. Scanning strategy effects. So which is one of the important thing to minimize the residual stress and anisotropy. That is the grain formation orientation. So there are a lot of things can be explored in this scanning strategy area. Similarly, how to minimize the residual stresses through preheating the powder or the base build plate. So those effects can be studied. And process parameter optimization, which is a very simple and important problem in the for the new grades, new additive manufactured grades. And similarly, reactive additive manufacturing is another area wherein we can work. We can design the composition such a way that during the 3D printing, it will form the kind of MMCs. And topology optimization for the designers to come up with a novel design which will optimize the weight and serve the purpose also. And another important area is the microstructure evolution modeling, like a face field modeling and predictions through novel models. This area is also a very important area because understanding the microstructure in the 3D printing still not mature. So how will the microstructure evolves like a forging process or a casting process? So this area is very important area to be explored. Power source. How about if I print a component with a laser or electron beam or electric arc, whether the property remains same or the microstructure remains same or defect generation remains same? No clarity. So there are chances that some kind of a laser may be beneficial for let's say steel, and electron may be beneficial for maybe titanium. So these also can be categorized. So this will help the designer to choose the right process, 3D printing process for in the coming days. And going to the next level, like printing the multi-layer materials or bimetal fusions and understanding the interfaces and its property and the defects evaluations. So these are the maybe the next level or the next platform where once we get the maturity in the ground level. And evolving, especially the industry, novel NDT technique is very, very important. Now, the advantage of this 3D printing is the complex shape. When I go for the complex shape, my coverage in the component through the conventional NDT techniques like radiography or ultrasound is very minimal. Like I may not be able to cover completely all the regions because of the complexity of the shape or surface reference issues. So how do I do without touching the component, like immersion ultrasound? Component will be somewhere and my source will be somewhere. So those kind of technologies currently required so that my inspectability with respect to the component should reach to 100%. That is ideal. If you look at the forging, you see the section thickness effect. Like if you take a 5 mm thick plate and 100 mm thick plate may not give the same property when you subject to the same heat treatment. Whether similar effects are there in the 3D printing, it's not clear yet, which we should understand. Then the higher end will be developing a functional materials like shape memory alloy or smart material development. And lastly, there are some impending problems like residual stresses, anisotropy, surface roughness issue, build size limitations. Like I said, like 400, and very few grades, about 15 grades are only 3D printing. So these are the areas where you academicians can focus and help us to create a database for us or the knowledge base for us, so that we can effectively implement this process for our country's projects and save a lot of money for foreign exchange for the country. I think I spent about 1 hour. With this, I just want to conclude my presentation, and I open the forum for the discussion. So any questions, please ask me. So whatever I know, I'll be happy to share with you. And I also share my email ID and phone number. So any doubt after the talk, also you'll be in touch with me. And I once again thank Dr. Kanmani and Dr. Keshavan for the opportunity. So this forum has really gave me a floor to express my thoughts, especially to share what I need from academicians. Thank you so much, sir.
Yeah. Thank you, Dr. Ram Prabhu. Actually, thanks for enlightening us on that, particularly, especially on what area we're supposed to work on additive manufacturing. I think your talk done a great justification, especially for last session of the this workshop. Actually, you started from basic and slowly move on to the.
Thank you, sir. Any questions? Yeah. People can drop in chat box also. I'll read and answer.
Am I audible, sir? Hello, Dr. Ram Prabhu, am I audible?
Dr. Subbu, you are audible to me. Ram Prabhu, sir, am I? Hello, Ram Prabhu, sir. Hello.
Ram Prabhu, sir, like we are talking, are you able to listen us? Are you able to hear us, sir? Kesavan, can you call it?
I'm just texting him.
Yeah, fine, good.
Just a minute, sir. My audio system just setting up.
Yeah, okay, please. Yeah,
just 2 minutes.
Yeah, please, no problem. Participants, meanwhile, please write your question in the chat box.
Sir, 2 minutes. I'm just
all right.
on my
no problem,
speaker.
Sir, please. Yeah, please.
Yes, sir. Now you speak, sir. I'll be able to hear you.
Yeah, yes, sir. Okay, fine. Yeah, thanks for your excellent talk. And then, your enlightenness in the area of where in which we were supposed to start to work from the scratch, even like materials and then properties wise. Even if you go further, in the certification, what the people are looking for, all those properties you mentioned clearly. I hope it's like a great input for all the participants, and then they can take it up forward and then start to work on. Yeah, with this small closure, I'll request the participants that please pose your question to Dr. Ram Prabhu directly. That means you unmute yourself and ask, or otherwise please put your question in the chat box. We will take it up. A participant, please, yeah. I think next session is a test, so everybody rigorously prepare for the test. Okay, I think there are many faculty members, sir, registered for the course, and then they've been attending for past 5 days, and then they're interacting a lot with us.
I could see from my contacts about 10 to 15 years.
Oh wow, great then.
Because the application has shared me, so I sent to others. So most of them are registered. Looks like.
Oh, really nice, really nice. Yeah, there is one question like.
He's asking the presentation, so he can contact me in mails, or I'll send him. No issues.
Okay, fine. Anyway, the video will be shared with you. So,
yeah,
since Atal, it will be there, so we can.
Yeah, sure.
So, any questions to Dr. Ram Prabhu? Yeah, please, sir. So, I met Dr. Ram Prabhu in one of the doctoral committee meeting in IIT Vellore. Okay, so the first impression itself, our impression is great. So, sir started to interact, and then we, within a short period of time, started to discuss about more technical stuff. So, there only I came to know about the importance of this residual stress. Okay, so in additive manufacturing, especially, there is a big problem. So how to reduce? So then, that time I started guidance of my MTech students here. Then slowly, then I said to sir, maybe I'll go further in that. So I just adopted the scanning strategies. That's why today morning also Dr. Samarjit has presented some case studies related to that. I understand that Dr. Prabhu used to help a lot. Okay, so since that's why he has given great opening to all. So see, actually, it looks like maybe we have to generate data, but this generation of this data is very, very important in additive management because we are having a lack of information about that. So once while generating the data only, we can understand the physics of the process. So the process mapping is important. The best of my knowledge, who are all working in additive manufacturing, one of their chapters, that means one of their objective is do that process mapping. Okay, based on maybe mechanical properties, based on maybe microstructural characterization, or so on. Okay, so in a nutshell, sir put everything. Then he said put number of ideas also. That is true that we have to generate because it's like huge void we have. Okay, so I think this kind of forum always help us to learn a lot in this direction. Okay, with this, yeah, you take it forward further. Yeah, somebody raise a question, sir. Dr. Yes,
sir.
Magibalan.
I'll read it out, sir.
Yes.
I think Dr. Prithvi has asked me the question. Can you share your polymer 3D printing? So as such, polymer usage in aerospace is very limited, very, very limited. And mostly, thermosets are used like, elastomers or some gaskets and seals, wherein 3D printing is not established yet. But what I understand is toy industries are some of the non-critical parts are manufactured through fused deposition modeling, which is a very famous process in polymer 3D printing. But as such, I have not worked much on polymers, but we have a group running who is making the machines for the polymers. So I have a little bit idea on that. But again, there is a limitation of number of polymers which can be printed. Like for example, you heard about ABS and other things. But coming to the thermosets like epoxy, the printing is not established yet. And can aluminum be 3D printed? As such, aluminum applications are very less. So it's in the form of alloy, I given you about 5 alloys which can be 3D printed. The problem with the aluminum is poor absorbability. In other words, a lot of scattering when you use a laser. So that's the one challenge you find in aluminum. Is functional grade aluminum metal matrix can be printed? So it's all can be done. That's what we are just started our 3D printing research in India. Still a lot of ground level establishment has to be done. Once we reach to that maturity, then we can go to the next level, making the nano grades or nano materials or the functional graded materials through 3D printing. At this point of time, going to that is not that advisable. I wish first we should have all our properties for the established grades to be established, so that the industry will use that to build a component and commercialize or popularize this process. Then we can take it to the next level, like functional graded and other things. So, can we use polymer lattice for adapter? See, again, in the aerospace, the designer will look at, this is my requirement. So what is the requirement? I look at what is the load acting on the component. Okay, if the load X, so then add the factor of safety and my polymer should have that much property. Second is, if a temperature is there, polymer cannot be used. Third is the operating environment, corrosion or the aging related issues. So polymer generally age. So the moisture content, other things you have to look at it. So based on that only the polymer or the metal or ceramics is chosen for a particular parts in the aerospace. So if you just ask the adapter, if it is a non-load bearing members, just for the only holding purpose, yeah, definitely polymer lattice can be chosen. 3D printing of high entropy alloy and application of aerospace. See, high entropy alloy through the melting process or the powder metallurgy itself not very well matured in India. So going to the 3D printing level, it's little challenging because you need a powder. So, and powder means not just a powder with certain characteristics. You need to have a spherical particle, you need to have a certain size distribution, okay, and the certain level of apparent density, tap density, or true densities are required. So when you meet the that requirement. See, making the powder is a costlier affair and difficult affair because you need to have a inert gas automation. But for high entry kind of things, you need to go much better, automation technique like plasma automation, so that the
I think internet issue, network issue, I guess. Still is, sir. Ram Prabhu, sir. I think now we may rejoin.
Is rejoining.
Rejoining, okay. I will make.
sorry, sir. I think some issue.
Yeah, sir. No problem. No problem. Please.
I am at, I think, high entry API.
Yes.
So,
yes.
Getting that powder, the high entry API grade powders with a high purity is a challenge. But as such, printing is possible or not, if you ask me, yeah, certainly it is possible. Because when similar alloys like super alloys or steels we are manufacturing, the advantage with the high entry alloy is you have a high temperature property also, or sub-zero temperature also properties are good. So that is the reason high entry alloy is most sought or most researched material recent days. What problems are usually faced during AM of refractory metal or alloys? So most of the refractory metals have a poor oxidation resistance. Unless your build ambience are not properly controlled, you will end up with forming the brittle components in your compounds in your refractory metal build. So that is one of the challenge. Second is the melting point. So we need to use the high energy lasers or high energy electron beams to print the refractory metals. Sir, I am seeing only this question before.
Yes, yeah. There is one question, maybe because of internet connection,
yes,
might have lost. Yeah, the question is, sir, like it's a general common question.
Yes,
research scholar work on a 3D metal printing, maybe thinking like it's cost effective. So how to justify that?
The question is whether is it a cost effective or not, or
he's saying that it's cost effective. Then in that case, how can we manage that one?
Okay. Sir, can you retype that question, sir? I am not getting the.
Just a minute. I'll paste it here for you.
Yes, sir.
Yeah. Yes.
Yeah, as common research scholar work on 3D printing metal, cost effective or not. So the what I understand is it is cost effective as long as you are able to see that you need a minimal material to do conduct your experiments. See, if you go for a fatigue or creep kind of studies, of course it is expensive at this point of time because you need more samples because scattering in the data are high. But if you want to run your project at a very low cost, then I would suggest go for the studies which involves a microstructure, which involves heat treatment microstructure, and understanding the tribological behavior or corrosion behavior kind of studies, where if you have a constraint on the cost, then you can work on those areas because where the material requirements are very minimal. But one point which I want to mention to all the research scholars, see, instead of working on process parameter optimization, try to get a metals which are printed to the optimized process parameter from the industry and work on building the data first. Once we establish this, then we'll go for the next level of new material grades and their process parameter optimization. Because at this point, there are a lot of work could be done on the currently printable alloy, for which the process parameters are optimized.
So no more questions, sir, from participants. Anybody would like to ask, please unmute yourself and ask also.
Sir, this is Dr. Jayan.
Yeah, please.
Yeah, please.
Sir, do you have any facility to print a ceramic?
Okay, see, ceramics, what I understand, I don't have a facility because I am working in a certification lab where there are no facilities, but I can see you what you can do. There is a company called Indo-MIN.
Okay.
It is called binder jet fusion. Binder jet technology. It's not a wafer based, it is a sintering based one, in which you can certainly do the ceramic materials printing.
Sir, your voice is not audible.
I think somebody, like, please mute yourself. Yeah, now it's okay, sir.
So there is a technology called binder jet technology, which is nothing but, extension of your powder metallurgy. Like, you don't have a mold, but you have a 3D printer to